Okay, so I want to continue with the discussion of hypothesis testing. All right, for today, we're going to talk about hypothesis testing for the population proportion. So before we start, there's a couple of conditions. Remember, anytime we're doing anything with the population proportion and we want to look at a probability distribution that's normal, we have to have some conditions met, right? The sample is a simple random sample. All right, the condition for a large enough sample is n times p times 1 minus p is greater than or equal to 10. And then the sample values are independent of each other. That is the condition that the sample size is not too large. So the sample size is less than or equal to 5% of the population. All right, so we will verify those conditions at the beginning of the first problem that we do. All right, now, when we talk about a hypothesis test, okay, what we're looking for is our sample data. Is our sample data enough to conclude that there is or is not a difference from the population? All right, so when observed values are unlikely, under the assumption that the null hypothesis is true, we say the result is statistically significant and we reject the null hypothesis. All right, so remember, our default assumption is always that the null hypothesis is true. All right, by saying the result is statistically significant or that it is unlikely under this assumption, all right, we're saying we have evidence to say that things might be different. And in that case, we can reject the null hypothesis. Now, to determine if a sample proportion is statistically significant, we have to build a probability model. Now, we have got three approaches to examining this probability model. The first approach that I'm going to look at is the classical approach. And the classical approach is basically the one that you can do by hand with a table and some simple calculator calculations. Okay. The second one is going to be confidence intervals, and I talked last time that there is a close relationship between this concept of hypothesis testing and confidence intervals. All right, both of those methods can be done by hand. The last one is the p-value method. Now, the p-value method can be done by hand, but it is best done by software. So the p-value method will set a problem up, and then I'm going to show you on the calculator how to continue on and evaluate that problem. All right. Okay, so let's start with the classical model. All right. Now, we may assume that a result is statistically significant if the sample proportion is too many standard deviations from the mean. All right. Well, from the mean, which is the assumed population proportion under this condition. So the idea here, what we want to do, right, we start with our basic hypothesis test, which the first part of this we actually talked about in the last video. All right, so you start with the sample is obtained by a simple random sample, where the data is a randomized experiment. You check that your sample size is large enough with this condition, and then you check that the values are independent of each other by checking that the sample size is less than or equal to 5% of the population. You determine your null and alternative hypotheses. All right, then we select the level of significance. Now, again, I told you for our problems, the level of significance is going to be given in the problem. We can question it or talk about it, but it'll be given for the problem. All right, the next step is we have to compute our test statistic. Now, our test statistic is the z-score. So remember yesterday, or the last video, right? The z-score was calculated with this formula here. Now, we're going to use, now the book says use table 5. I'm going to use table 7 to determine the critical value. All right, and we'll talk about the difference in the tables in a minute. And then we compare our critical value to the test statistic. All right, so depending on the type of hypothesis test we have, two-tail, left tail, or right tail, we're looking to see whether or not the critical value, the critical value is the cutoff. Our test statistic falls in the critical region or not. All right, so in the case of a two-tail test, that would mean that our test statistic would fall either into the left tail or the right tail. For a left tail test, it would fall into the left tail, and for a right tail test, it would fall into the right tail. And if that is true, then we get to reject the null hypothesis. If our test statistic falls outside of the critical regions, the tails, that is in between here or this side or this side, all right, then we don't have a result that's statistically significant, and we can't reject the null hypothesis. And then the last step is to state the conclusion. Right? So I pulled two problems from the back of the textbook, and we are going to work these two problems. It occurs to me I should have separated them a little bit more, but that's okay. All right, so let's read through the first problem here. All right, in December 2001, 38% of adults with children under the age of 18 reported that their families ate dinner together 7 nights a week. In a recent poll, 403 out of 1,122 adults with children under the age of 18 reported that their families ate dinner together 7 nights a week. Has the proportion of families with children under the age of 18 who eat dinner together 7 nights a week decreased? Right? And use an alpha of 0.05. Okay. All right, so I'm going to do some writing down here on the bottom. So this is problem number 20. Hang on, where is... Okay, once again, get the stylus the right way up. Okay, that's better. All right, so this is for number 20. All right, so I need to pull some information out of this problem before I start working on it. And again, just for the sake of saying it, not every number in the problem is significant to solving the problem. All right, in December 2001, 38% of adults with children under the age of 18 reported that their families ate dinner together 7 nights a week. All right, the only thing that's important to there is the 38%, because that is the proportion that we are starting with. So that is our P. All right, so P is 0.38. That is going to be what we're assuming is true until we can show otherwise. Okay. In a recent poll of 403 out of 1122, all right, so my sample size is 1122, and my X is 403. All right, so, and then the only other piece we need out of that is the alpha. So my alpha is 0.05. All right, now, how are you going to determine your null and alternative hypotheses? Well, the null hypothesis is always the same. The null hypothesis is your statement of no change. So that means that the population proportion is 0.38. For the alternative hypothesis, all right, you have to read what they're asking, and that's always going to be the question that they're asking. Has the proportion of families who eat dinner together 7 nights a week decreased? All right, so remember, decreased means less than. So is P now less than 0.38? That's what we're trying to see if we have evidence for. All right, so I like to draw a picture for these. I also like to not make random marks on my board. Okay, actually, let me move up now because I don't need the problem for anything else at the moment. So give me some more room here. All right, so let's do this. Let's get a nice normal curve going here. Yeah, that's actually not too bad. All right, so because we're interested in the proportion decreasing, right? Less than is always to the left. So I am going to shade in the left tail because that is going to be my critical region. So when I calculate my test statistic, if my test statistic falls out here, I'm going to reject age 0. If it falls in here, I'm not. And just so that I remember, I am going to call this region do not reject age 0. This way, I won't forget. All right, so now we need two things. We need to know the critical value here. And we also need to know our test statistic. All right, so before I do anything, let's calculate our sample proportion. All right, so remember, p hat, our sample proportion, is going to be x over n. So that's going to be 403 divided by 1122. And I am not going to try and do that in my head. So thank you, 403 divided by 1122. Okay, so notice I get a long decimal there. I want to round p hat to the same thing p is rounded to. All right, so if I'm going to do that, then my p hat is going to be 0.36 rounded off. So 0.36. Okay. All right, so I've got my p hat. I need to calculate my test statistic. All right, so my test statistic, z, is going to be, right, what do? I do my data minus the mean divided by the standard deviation, which is a calculation, right? So my data point is 0.36 minus the mean. And remember, for the probability distribution for the binomial, the mean is the population proportion. So it's going to be 0.38. And then I have to divide that by, all right, underneath a big square root sign, which I'll put in a minute, I want to do p. So it's 0.38 minus, times 1 minus p, 0.38, divided by n, which is 1122. All right, and that whole thing is under a square root sign. All right, now again, because of the way this calculation is going to come out, I want to do the whole thing in one shot on my calculator. Otherwise, I'm going to kick into scientific notation, and I'd rather not do that. All right, so in parentheses, in the numerator, or just do that part in your head, 0.36 minus 0.38 divided by, and then I need a big square root. All right, so on top, 0.38. You could do 1 minus 0.38 first if you wanted to. I'm just going to put it all in. 1 minus 0.38. Close the parenthesis for the numerator. Divided by 1122. And then close the parenthesis for the square root. And I get, again, round this to... All right, for these problems, for all the hypothesis testing problems, I'm going to recommend that you round your test statistic to 3 decimal places rather than 2 like we would normally do. So minus 1.38. And actually, the next place is a 0, so it doesn't matter whether I round it to 2 places or 1 place. All right. All right, now I need to get my critical value because that's going to determine whether this number falls on this side or this side. All right, so to do that, I need my textbook table. And let me pull that into view here. All right, so when we're dealing with probability distributions for the proportion, we are always using z. Okay? Always. We don't have to worry about the degrees of freedom or anything, which means I'm going to want to go to that bottom line on the table there that says z. All right, so 0.05, we already know what this is because we did it a lot in the last video, is 1.645. All right, so I'm going to get that out of the way. All right, so 1.645. Now remember, this is on the left, so on the left it's actually a negative. Okay, stop that. It's actually a negative 1.645. All right, so now I can place my test statistic. Now I have a marker that makes this a number line. So negative 1.3 is going to be less than negative 1 or greater than negative 1.6, right? So it's going to fall somewhere on this side. Right? So we end up with our test statistic being greater than our critical value for a left-tailed test. All right? You don't have to remember that if you have a picture. This is why I like to draw a picture. All right? Basically what this tells me is my test statistic falls in a do not reject region. All right? So I can make the conclusion this way, that I'm do not reject H0. All right, so what does that mean? Well, let's think about what I said before about our test value being enough standard deviations from the mean to call it unusual. All right, in order for our test value to be enough standard deviations from the mean to be considered unusual, it would have to fall out here on this side, because this is our cutoff for unusual under these conditions. So because I didn't fall out here, all right, that means that the evidence that we collected is not enough to support the claim. All right, so the very last thing you have to do here is actually write down your answer, because this isn't your answer. This is a step. All right, so your answer is the conclusion written out. So in this case, there is not enough evidence to support the claim and I'm just going to stop there. There is not enough evidence to support the claim. If you want to finish that sentence, you would have to restate what the problem is claiming, right? There's not enough evidence to support the claim that families with children under the age of 18 eat dinner together 7 days a week less than they used to. Okay, so you would go back up here and basically just restate this. All right. All right, so when we're dealing with a one-tailed test, and that's the difference between these two problems, which I'll get to in a second, right? The difference between a one-tailed test and a two-tailed test is the fact that we used alpha here, right? All of alpha falls in one tail. All right, that makes it easy because I'm just using alpha. All right, so let's look at the next problem. All right. The next problem says, in 1994, 52% of parents with children in high school felt it was a serious problem that high school students were not being taught enough math and science. In a recent survey found that 256 of 800 parents with children in high school felt it was a serious problem that high school students were not being taught enough math and science. Do parents feel differently today than they did in 1994? Use the alpha equals 0.05. All right, so again, it's a similar type of question. The difference is in the question, right? Because the question up here was asking whether what they're interested in had decreased. Here, they're just interested in whether it's different. All right, so they don't care if it's increased or decreased. They just want to know, is it different? All right, so we need to pick up. All right, and I've had this here long enough. I'm going to do this. Okay, so let's pull the information out of this problem here. So let's go back to the beginning. In 1994, 52% of parents with children in high school felt it was a serious problem that they were not being taught enough math and science. All right, so that is going to be our P. This is what we are going to assume is true until we find enough evidence to refute it. Okay, so 0.52. Let's see. In a recent survey, 256 of 800 parents. So there were 800 parents surveyed. So that is going to be 800. And 256 of them answered the question in what we would consider to be a success. So that is our X. All right, do parents feel differently today? Use an alpha of 0.05. So alpha is 0.05 again. Okay, so let's set up our hypotheses. Always the first step. So H0, again, you shouldn't have to think about H0 because H0 is always going to be written right here. Our null hypothesis is that the proportion is 0.52. Our alternative hypothesis, we have to go back to the question that's being asked. All right, so the question being asked is, do parents feel differently today? So again, not more, not less, just differently. So differently is not equal to. So when I come over here to draw my picture, right, not equal to is going to be a two-tail test. So that means maybe it's lower, maybe it's higher, maybe it's not different at all. All right, so this in between here becomes my do not reject region. All right, so I'm going to have to find two critical values, but I'm really just finding one because remember, this is symmetric. All right, now I need to calculate p hat. So I'm going to come over here. We need to do p hat, which we saw before was x over n. Okay, so that's going to be 256 over 800. So 256 over 800 is 0.32. Really? Wow, that's really low. 0.32. 0.32. I didn't make a mistake there. No, I didn't. And I read that right. Yes, I did. Okay. Now, let me answer a question that some of you may be thinking of right now. And that is, if I know that my sample statistic is lower than 0.52, why am I bothering with the two-tail test? Why don't I just do a left-tail test? Well, the reason for that is the order that you do a hypothesis test in. All right, when you're actually doing clinical research, all right, you develop your hypothesis prior to collecting evidence. That's the way you do it. So prior to collecting the evidence, you don't know if it's going to be higher or lower. Again, you may be particularly interested in one over the other, in which case you would say a left or a right tail. But if it doesn't matter to you whether it's higher or lower, you're always going to do a two-tail test. So the test is determined before the data is collected. All right, and that's why, even though now I can see that this is lower than this, so I know my results are going to be over here somewhere, I am still staying with the two-tailed test because that is what the hypothesis was set up to be initially. Okay? All right, so let's calculate my z value, right? So z is going to be my data value, 0.32, minus my mean or population proportion, divided by, and then I have to do this calculation again, right? 0.52 times 1 minus 0.52 divided by n, which is 800, and then the whole denominator under a square root sign. Okay. All right, so I'm going to come over here, clear that and make room. All right, so again, numerator in parentheses, 0.32 minus 0.52 divided by big square root on top, 0.52. 1 minus 0.52 is 0.48, so I'm just going to say times 0.48 divided by 800, close the square root, and I get, okay, something pretty dramatic. All right, minus 11.323. Okay. Now, I'm going to look the critical values up on the table, all right, but I can pretty much at this point, I think I know what's going to happen. Now, here's the thing. All right, they give us an alpha value of 0.05, but that alpha value is split between these two tails. So the sum of these two tails is 0.25. So each one of these tails is an alpha over 2. All right, and since what I'm looking up is, again, this cutoff score for this one tail, all right, I need alpha over 2. So that is going to be 0.05 over 2, or 0.025. All right, so anytime you're doing a two-tailed test, you have to divide alpha by 2. A one-tailed test, you use alpha. A two-tailed test, you divide alpha by 2. All right, so let's get our book back here. Hang on. Let's get our book back here. Where is it? There it is. And now I need to look for alpha 0.025. Okay, and I'm going to go down to the bottom of that column and I will see 1.96. Okay, so my cutoff is 1.96. So that means on the left it's a negative 1.96. On the right it's a positive 1.96. So where does my z-value fall? Well, I think my z-value falls kind of off the board here, but I will not worry about scale and say it falls on this side, negative 11.323. All right, so again, what this means is, well, first of all, it means I did not fall in the do not reject region. I fell in the critical region. That means I get to reject H0. All right, so let's look at what that means. All right, so remember, we're trying to determine whether our test value is too many standard deviations from the mean, right? Is it far enough from the mean that we can call it an unusual result under the assumption that the null hypothesis is true? All right, and in this case, yes, it's way outside. It's not just unusual, it's enough to say that things have changed. Okay, we are 11 standard deviations from the mean. Our cutoff is just about 2 standard deviations from the mean. All right, so this is definitely a statistically significant result. All right, so in the case where we reject H0, we say there is enough evidence to support the claim. All right, now I would finish that. I'm going to end the sentence there, but I would finish that sentence by stating the claim, right? There is enough evidence to support the claim that parents do feel differently today than they did in 1994 about whether high school students are being taught enough math and science. Now, this is dramatic enough, right? The difference is dramatic enough that I can not only say that they feel differently, all right, I can say that the attitudes have changed in that fewer parents feel that students are not being taught enough math and science. All right, so this was a dramatic enough result that we can say that that proportion has, we have evidence to support that this proportion has decreased in the last, I don't know when this was, I'm trying to think when this book was published that I got the problem out of, but, 2006. It says right here, 2006. All right, so from 1994 to 2006, attitudes have changed actually rather significantly about that. All right, so there are a couple of examples there on how to use the classical method and just a basic calculator, right? We didn't need anything really fancy. You just need to have a student t-distribution table handy. Okay. All right. Next on the list, all right, and let's look at this in terms of a confidence interval, okay? I'm going to turn the discussion around a little bit. We have all the work done that we need done, okay? We don't need to do anything else, all right? Now, if I was going to do a confidence interval here, all right, let's think about that for a minute. Yep, I keep doing that. Confidence interval. Now this is a good one to do with a confidence interval because it's actually a two-tailed test. All right, so we're used to confidence intervals being two-tailed problems. Okay, so what do I need for a confidence interval? I need all of the stuff that I have for my sample, right? So I need my p-hat, which we figured out was 0.32. I need to calculate the margin of error, right? So the margin of error is equal to z alpha over 2 times, and then we do the standard deviation calculation, right? And we use p-hat to do it. P-hat, 1 minus p-hat, over n. All right, so I'm going to have to do this calculation. Now, the z alpha over 2 we have already. It's 1.96, right? So z alpha over 2 is 1.96. All right, so if I come over to my calculator, all right, so I'm going to do 1.96. and then big square root. All right, so p-hat is 0.32 times 1 minus 0.32. Close that for the numerator, divided by 800, yes. Close the square root. We get 0.03, and for these we were using the same number of decimal places as everything else, so that's 2 decimal places, so 0.03. All right, so the confidence interval, okay, the confidence interval for the population proportion is going to be on the left side, right? Here, let me do lower bound, upper bound like I did before. Lower bound, upper bound. So the lower bound is going to be p-hat minus e. So that is going to be 0.32 minus 0.03. And then the upper bound is going to be p hat plus e. So that's going to be 0.32 plus 0.03. So that is going to be 0.29. And that is going to be 0.35. All right, so we have a confidence interval of 0.29 to 0.35. Okay. All right, so there's my confidence interval. Now, what I want to do is take a look at my population proportion and determine whether I've captured it or not. All right, so if my interval is going from 0.29 to 0.35, right, if we think of this on a number line here, right, 0.29 on the low end, 0.35 on the high end, where is my population proportion? Well, that's fallen like way out here. All right, so 0.52. All right, so my confidence interval did not capture my population proportion. All right, which means, all right, think about, again, we have to kind of think back to confidence intervals here a little bit, right? If I am doing a 95% confidence interval, that means I can be confident that 95% of the confidence intervals that I produce will capture the population proportion. So in this case, it didn't, which means I have one of those confidence intervals that falls into the 5%. All right, I have one of those confidence intervals that falls into the unusual category. All right, so if your population mean falls outside of your confidence interval, or your population proportion in this case, falls outside of the confidence interval, then you can reject H0. Now, in terms of validity of results, it doesn't matter which of these techniques you use. All right, doing this technique or doing this technique will give you the same result. All right, there's absolutely no difference. It's just a matter of the type of work you want to do. All right, I kind of like this method just because it does make use of the normal curve and it does make use of the probability model a little more than this one does. But in terms of the results you'll get, either one of these are fine for a method for doing things by hand. All right. All right. So classical method, confidence interval method are good methods when you have pen, paper, and a basic calculator. Okay, and a student t-distribution table. All right. Let's take a look at technology. What can I do using technology? All right, now if I'm going to do this process using technology, all right, I have to think about it a little differently. And the reason for that is the technology is not going to go through and do all the fiddly little calculations. The technology is going to make use of the fact that our definition of alpha is the probability of making a type 1 error. Right? So if alpha is the probability of making a type 1 error, we can then compute the probability that using our sample, we make a type 1 error. And then we compare those two probabilities. Okay? All right, so when we do hypothesis testing using the p-value method, we're not losing any of the setup information. We still have to do all the confirmation stuff, which I actually didn't do for that problem, but I'm going to leave that as an exercise. You can show that that's the case. And then you're still going to determine your hypotheses because you need that. You're still going to select your level of significance, or you will be told in the problem what your level of significance is. All right, and then what we're going to do now, the textbook actually goes through this by hand. I am going to show you using the TI-8384, actually it's a TI-84 calculator, okay? So, here's what we're looking to do. All right, we're looking to compute the probability of making a type 1 error based on our statistical sample. All right, so that is what we're calling the p-value, and I realize there's a lot of p's involved in this. All right, so just be careful. P-value. All right, it's the probability that the statistical data, the statistical sample, will result in a type 1 error. Okay. All right. So you could do this by hand. You would have to do, basically you would do a normal probability problem. And then you would compare what you get to your alpha value. All right. So what we're looking for is, we're looking for a p-value to be less than the alpha value to be able to reject the null hypothesis. Because what we're saying in that case, all right, and that's what this says up here, if the p-value is less than the alpha value, that means our statistical sample will yield a smaller probability of making a type 1 error than we are allowing for. All right, and that's a good thing. All right, that means we get to reject the null hypothesis. That means we have an event that is unusual under the assumption that the null hypothesis is true. All right, now we are not going to calculate p-values by hand because for me that's a nightmare. I just don't like doing it. And it is a technique that the calculator is more suited to. So here's what we're going to do. We're going to go back to our second problem here, since this is the one that I have all the information written out for. And in fact, we have it written out twice. All right. And I'm going to go to my calculator. So let me clear this out. All right, we're going to use the we're going to go into stat. I didn't prep this ahead of time. And we're going to go to tests. All right, now notice there's a whole bunch of tests here. What we're interested in is a z-test. All right, because that's what this is considered. We're using a z-sample statistic, and we're using a z-cutoff, all right, or critical value. All right, so I'm going to pull up the z-test. I'm going to get a menu. Now, I have two choices here. I could use data. If I have data input under the stat edit L1, all right, I could use data. But I don't have data here. What I have is I have stats. All right, so I'm going to go over to stats, and I'm going to highlight that. And now notice it's asking me for some... Oh, wait a second. I just realized. Hang on. Time out. Let me go back in for a second. We are doing a proportion z-test. Here we go. It's like it was asking me for the wrong information. We're doing a proportion z-test, right? We'll do the z-test next time. Proportion z-test, okay? So for a proportion z-test, you're not going to get asked for data. All right, so I need to put in my p0. That is my population mean, my population proportion. So that is 0.52. I need to put in my x value, right? So x is 256. And I need to put in n. N is 800. Now, just a side note here before I go any further. If you're given p hat instead of given x and n, right? Some problems you'll see just will give you p hat. But they also have to give you the sample size. So if you want to go to the calculator to do this, to get the x, just multiply p hat by the sample size, and that'll get you the x. All right, to solve that. Now you have to choose your test. Am I doing a two-tailed test, a left-tailed test, or a right-tailed test? So in this case, I'm doing a two-tailed test, so that's the default. All right, I could move it over. If I was doing one of the others, I would just move it over and hit enter to the one that I'm doing. All right, so that's right. And then calculate. All right, now notice what I get here. Okay, this reminds me of the test that I'm doing, that the proportion is not equal to 0.52. It gives me the z-value that I calculated over here. All right, so I got that negative 11.323 rounded off. It gives me a p. It gives me my p hat. All right, now this p here is the p-value. All right, so let's talk about this for a minute. The p-value is given to you in scientific notation. This is not unusual. All right, you will never have a p-value that is greater than 1 because the p-value is a probability. All right, so if you see a p-value greater than 1, automatically you are in scientific notation. Okay, so what does this mean? Well, this means I have 1.04 times 10 to the negative 29th. So that means there are 28 zeros before this 1 after the decimal point when I adjust for that. I'm not going to try and write that down. All right, basically the p-value here is 0. All right, for all intents and purposes, the p-value here is 0. So we're comparing that to an alpha value of 0.05, right? So my p-value is less than my alpha value of 0.05, so that leads me to this conclusion. I can reject H0. Now this is so dramatically small because the difference here was considerable. All right, if I come back up to, let's come back up to this one. All right, to the first one. I don't need to do any more work on paper to do this one using the p-value. It's one of the nice things about the p-value method. There's very little that you have to work out. All right, so let's clear this one out of the way. And let's go back in again, stat, tests. All right, 1 proportion z-test. You'll see there's also a 2 proportion z-test. That is for comparing 2 population proportions. That's not what we're doing, okay? So 1 proportion z-test. Now all the information from the last test is going to be in there, but I'm just going to overwrite it, okay? So our population proportion was 38%, so that is 0.38. The x from this sample, hang on, was 403. And my sample size was 1122. All right, now what was the test I was doing? Well, we go back to the question, right? We want to know if our proportion has decreased. Decreased is a left tail test. So I'm going to come over here and highlight left tail, or less than. And I'm going to calculate. Okay. All right, so again, notice I get my z, I get my test, I get my n, I get my p hat, and then I get my p-value. All right, so I'm looking here at my p-value. My p-value is 0.075 or 0.08. All right, what was the alpha that I was comparing that to? 0.05. All right, so in this case, my p-value of 0.08 is higher than my alpha value of 0.05. All right, so in a case like that, right, we're saying this result is not unusual given the assumption that the null hypothesis is true, so we do not reject H0. If the p-value is greater than the alpha value, all right, then that means that based on your statistical evidence, you have a higher probability of making a type 1 error than you're allowing for. All right, so you do not reject H0 in that case. All right, so those are the 3 methods that we're going to be talking about for the next couple days, but specific to the population proportion.